Hi, hello everybody. We are looking at lesson 10, functions and their graphs. We're going to do some more with function notation here, evaluate and simplify the difference quotient. This is the foundation of calculus right here. So we're starting just to work with notation and learn the skills to simplify, what I will introduce a little bit later as the difference quotient. We will talk about transformations and quick sketches of polynomials, things you've hopefully know and understand and have learned before. So we'll see if we get to that. We'll talk about it later, surely. You have a Delta Math assignment at the end of today. And again, I'm probably going to try to go a little bit fast because these videos literally take an hour to process. So I'm going to remember, you can pause the video and rewind as much as you need to. So please take advantage of that. Example 1, evaluate the piecewise function. Make sure that you are writing down the directions. This is an example. F of x is an example of a piecewise function. And this is one thing, this notation, f of x, it's how we read it, f of x. And it's really important that you get used to using the notation. I just had a faux pas where I said, this is an example of a piecewise function. And in AP Calculus, that's going to be a bad explanation. You want to actually use the word. Instead of this, it would have been better for me to say, f of x is an example of a piecewise function. And so when you're writing your free response questions in AP tests, they want you to be very specific and actually use the language is graph F. Don't say the graph, say the graph of F or the graph of G or H of X, F of X. You have to use the language, okay? So what it is we have the function itself here, which is x squared plus 2. We know the shape of that is a parabola, but this is the condition where x is less than or equal to 1. So normally, if we were to graph this, this is a parabola that's been shifted up 2 units. So normally, it would look like this kind of parabola shape shifted up 2 units. But we only want to see the parabola for values on the x-axis that are less than or equal to 1. So right here, where our parabola has an output when x is 1, we want to see everything to the left of that x value, which means I don't care about the stuff on the right, hence the eraser. Gotta love the eraser. Okay. Our second part of this piecewise function f of x is this output of 3. And 3 is a horizontal line like that. There it is, y equals 3. That's the line that extends left and right forever and ever and ever. And we only want to see that line for x values greater than 1. So it turns out they overlap here. I didn't plan on that. That just sort of happened. That's a coinky-dink. But we want x values greater than 1. Greater than 1 is everything to the right of 1, like 2 and 3 and 4, but also 1.1 and 1.01 and 1.0001. We are infinitely close to this point right here, and then it turns here to the red graph. I don't care about that red line to the left of 1. I only care about it for x values greater than 1. This is the piecewise function, and you can see that we have the x squared plus 2 parabola to the left of 1, and then the line to the right of 1. So the question is, we want to find f of 1. Do you have to draw the graph to do that? No, you don't. You can look at the condition. Always look to the condition first. Here, they're saying x is equal to 1. So which do I use? Can I use the top or the bottom? Well, x is equal to 1 for the top equation. So that's what we're going to use. We're going to plug in the 1. 1 squared plus 2 is 3. And that is the best way to write it, f of 1 equals 3. This is function notation. We love function notation because it says the input was 1 and the output was 3. And that's the ordered pair, 1, 3, on my graph. How about that? Kind of nice. Here we have the x value equal to 1.5. And so again, the question is, which equation do we use, top or bottom? Well, x is 1.5. 1.5 is greater than 1. Here, if we tried 1.5 for x, 1.5 is not less than 1. That is a false statement. We can't use that. Here is the true statement. And so we would take this equation in red. There's nothing to plug in. It's just 3, always 3. I don't care what your x value is, the output is 3. And that's it, okay? So pay attention to the condition, and we're going to talk a lot about conditions in AP Calculus because a lot of what you're doing is going to be, you have to set the condition first. If this is true, then we know this, and that's called the conditional statement. So we want to make sure that the condition is true first, then we can do the rule or the definition or the theorem or whatever it is. But this is a huge part of AP Calculus. So example 2. Evaluate the function f of x equals 2x squared plus 7 at the given values. Again, good idea to highlight those examples, write the directions. Again, we have more function notation. This says, go to your f function. Sorry, let me move that down just for a little minute. There you go. Go to your f function. There it is. And this is saying your x value is now going to be replaced with a 3a. So in order to do that, I'm just going to use blue. So we have f of 3a. That says go to your f function, and then wherever there was an x, you're going to replace it with 3a. And so I like doing this. I sort of do a fill in the blank. We're no longer using an x, so instead of an x, I'm going to use a blank space and fill it in with 3a. And then I can simplify. So order of operations here is we have 3a being squared. How many of you think that's 3a squared? That's a common mistake and totally incorrect. So 3a times 3a is 9a squared. Be very careful. So we have 2 times 9a squared, which is going to be 18a squared plus 7. And that's f of 3a. And that's all we can do. This answer is going to be in terms of a. And this is just learning how to simplify. Here, our x value in this case is b minus 1. Everywhere we see an x, we're going to plug in b minus 1. So we want to do f of b minus 1. So I'm going to go back to my equation, and anywhere there's an x, I'm just going to leave a blank space. Instead of x, we're plugging in b minus 1. Now this is really, really tricky. What is b minus 1 quantity squared? How many of you said b squared minus 1? That would be incorrect. When in doubt, write it out, ladies and gentlemen. This is square the entire thing. Just the same thing here. It would be 3a times 3a. Repeat it 2 times. 3a times 3a is 9a squared. Here we have b minus 1 written 2 times. Well, now you see that it's a binomial being squared, and you need to multiply that very, very carefully. I'm going to leave the 2 for a minute, and I'm going to distribute b squared. The outside is negative 1b, and negative 1b makes negative 2b plus 1. I hope you know that. You should at this level. I don't know how many times we've talked about it. We're going to distribute the 2. So we get 2b squared minus 4b plus 2, and then combine like terms. So f of b minus 1 equals 2b squared minus 4b plus 9. You need to be so good with this. All of these steps, these squaring a binomial, you should know how to do that now. There's absolutely no excuse. Do not miss this. I will be so disappointed. I'm just kidding. I will still love you. It's fine. But we're going to try and fix those mistakes because, boy, will you kick yourself on the AP test if you do that. Here, this is kind of an interesting one. This is saying we're going to do 4 times f of 3c now. I will 3c. So it's kind of an interesting thing. I'm going to write it just a little bit differently. So this is ultimately, when we're done, we have to multiply everything by 4. That's sort of what that's saying. And here, this says your x value is going to be replaced with the 3c. So, and it's saying go back to your f function and plug in that 3c. So I'm going to do that. I'm going to leave this 4 for later. And we're doing 2x squared plus 7, but we're not using x. We're going to fill it in. X is going to be the same as 3c this time. All right, so we already did that. What is 3c? Quantity squared. 3c times 3c is 9c squared. That's going to get multiplied by the 2. So we get 18c squared plus 7. I can't do anything more than that, but we still need to multiply the whole function, the whole entire thing by 4. I don't know what 4 times 18. 4 times 20 is 80 minus 8. So 72c squared plus 28. So 4 f of 3c equals 72c squared plus 28. Hopefully my math was right. And again, one more here. This one's a little different. What is this symbol? We talked about it. That's right, delta x. So delta x, and again, here's another delta x. We're just going to use it. It's a symbol. We're going to use it. And again, this is saying everywhere you see an x, you're going to replace it with x plus delta x. And delta x is just a change in x, some small change usually in the x. So just sort of adding a little bit to the right, adding a little bit more, and we'll talk more about that later on. And this is kind of interesting notation. And so this is the difference quotient. You can see here's the difference part, subtraction, and it's a giant quotient. Right? Quotient is the answer to a fraction. All right. A division problem. So this is 2 things. I'm going to color code this. I'm going to use green, red, and blue and show you the first thing here. I'll do in green. So this says go to your f function. There it is right there. And replace your x's with x plus delta x. So I'm going to write 2, my function with a blank space. And in that blank space, we're plugging in, we're plugging in x plus delta x. You could plug in anything. Maybe they're going to have you plug in h plus c, or maybe they're going to have you plug in h or x plus h. There are tons and tons of ways we can do this. You just plug in what they tell you to. It doesn't matter what the letters are. Just plug it in and proceed. Then there's the difference sign here. So big, I'm going to do just black. And then f of x. What's f of x? F of x is this. So we're going to subtract that entire 2x squared plus 7. We don't have to change anything. That is f of x. We're subtracting the function f of x. You'll notice I'm subtracting the entire function. This is where most mistakes happen. Do not forget to distribute your negative. Please, please, please. The denominator does not have an f in front. It is not commanding you to do a substitution. It's simply delta x. Pretend it's a b. All right. Doesn't matter what it is. So I'm just going to leave that delta x. Nothing to do there, nothing to plug in, nothing to substitute. I'm going to go ahead and we're going to expand this binomial. Lots of room here, lots of space needed. I have to do this first. Remember, there's 2 of them, x plus delta x, and this could be confusing. X plus delta x. Hopefully you won't have very many of these. X times x is x squared. X times delta x, and another x times delta x is 2x delta x. And then last times last is, I'm going to write it, delta x squared in parentheses. Then don't forget your plus 7. And then I'm going to distribute my negative minus 2x squared minus 7. Be very, very careful distributing that negative. And we still have this delta x in the denominator. All right, I can go ahead and distribute my 2. That's going to give me 2x squared plus 4x delta x plus 2 delta x's squared. And what happens with your plus 7 and minus 7? Hey, those clean up nicely. Minus 2. Oh, look at that. I'll cancel that out on the next one. All over delta x. Another thing happens to cancel out. Yay. That should happen. If it doesn't happen, you probably made a mistake. This is the whole point of the difference quotient, is that it'll clean up. All right, so we have 4x delta x plus 2 delta x's squared, all divided by delta x. And I'm going to go ahead and say my favorite way to do this is to remember that delta x is dividing every single term. So I'm going to break that up. Delta x, and some stuff is going to cancel here. Delta x on top and bottom reduces to 1. Delta x squared divided by delta x is going to cancel out one of those. And so we're left with 4x plus 2 delta x. And that, folks, is as good as it gets. All right, so this is a big, just how do we simplify this stuff? So we get a little bit of practice now, and we're going to do it again later, okay, with the real calculus. If you have questions, it's a good time to write it down, highlight it, ask me the next time we are Zooming, or come to office hours. All of that's in the unit calendar. Example 3, make a guess about the shape of the polynomial. This is so important throughout mathematics. I've always told my students that you need to remember, what does it look like? If you have a picture in your head, you can use that to help determine if your answer is valid. So we want to keep that in mind. We want to make a guess. All of these are polynomials, regular, nothing fancy functions. I love them. They're fantastic. When in doubt, graph it out. You can all put these in your calculators. How do we know the shape? The shape is determined by the leading term. The leading term is whatever the highest power of the function is. So the highest, H-I-G-H-E-S-T, the highest power tells us so much about a function. And so that's what we want to keep in mind. Now, all of these happen to be in general form, where everything is nicely in order, like all my ducks are in a row. So all of these were nicely given to you so that the leading term actually is leading. But always just look to the highest power. So here is my leading term, a positive x squared. What shape is that? Parabola. You know that. It's x squared. It's always a parabola. What about this one? Negative x to the 4th. That is the leading term. It tells us so much. When in doubt, graph it out. I will tell you, though, it has an even power. Its arms up just like an x squared. If it's got an even power, the arms are always going to match. They're either going to be arms up or arms down. The negative makes it arms down. Okay, I don't care what it looks like in the middle. If you were to go and graph this, maybe it looks like this. We don't really care about the middle. We just care that the arrows all point down to infinity, not negative infinity, rather. Okay, so whatever it is, the shape in the middle, we're not too concerned with right now. We just want the overall, where do the arrows point? Do they all point up or do both point down? So what happens when our leading term is odd? I always said it was odd arms, so one is up and one is down. And we want to know which one is it, okay? So this one happens to be positive. So if we were to graph this function, it's probably looking something like this, increasing. going uphill from left to right. Now, maybe if you were to actually graph it, it looks something like this. I don't care. I don't care what it does in the middle. The arms start low on the left and end high on the right. Low on the left, high on the right. Here we have negative 4x to the 5th. Again, I don't know the shape of this thing, but I know the leading term has an odd power. So it's odd arms, and we don't know which one it is. So this has a negative in front. So it should be going downhill from left to right. So it starts up high, ends down low. We always read from left to right. And maybe if you were to actually graph this, it might have some more bumps in it, like that. I don't know. Like I did this like a month ago, so I don't remember what it looks like, but you can put it in your calculator and verify. But we know that it starts high on the left and low on the right. And that's what we want to know. That is huge information, okay? And that's all just, is it an even power, positive or negative? Is it an odd power, positive or negative? All right, it's a dance. Okay, let's keep going. Hopefully you know all that, and that's nothing new for you. Transformations. Again, pause the video and maybe get yourself a nice looking graph. Doesn't have to be beautiful, really. No, don't take time. Don't take excessive, exorbitant amounts of time. I would call it a chicken scratch graph. All right, use the graph to sketch a graph of each function. So first thing we should know is this should have had a label on it, and I couldn't make it work. This is the graph f of x. It's a generic graph. You are going to see these all the time. Do you know why? You can't put it in your calculator. You can't cheat. You have to know how to do this stuff on the AP test. And there are so many of these because they know your calculator can't handle this. Your brain is the only thing that can do this. So this is our function, our generic function f of x. And we have these simple transformations. And these are all transformations that we did last year in pre-cal. Hopefully you remember them. And we're going to just refresh our memory so that when you see these kinds of transformations, you remember what they do. So here's the first one. We see that we had the function f of x, but they've changed something. Well, now there's an x minus 3 inside this function. So what happens? And I wrote that down because I could hear you all talking to me. It was amazing. It's like so cool. You know, the space-time continuum, we met somewhere in the space-time. Okay, I'm full of crap. So I know you said that the x minus 3 always shifts the graph to the right 3. Remember, everything with x is always opposite. And so even if you think it's x minus 3, it's going to shift it to the left 3, but it doesn't. Everything with x is opposite. So we're going to go ahead and we're going to do that. I'm going to try and color code this. We're going to shift right 3. So all I have to do is take maybe this point and shift it 1, 2, 3, and it's to the right. And I'll take this point and I'll count 1, 2, 3 to the right. And so this graph got shifted over, and it's not fantastic, but this point here got shifted 1, 2, 3. Okay, so like that. So this is, I'm going to just label it with the A there for letter A. Okay, so there you go. Well, what's this 4 going to do then? So this 4, the difference is here we were inside. Everything that's inside with x shifts in the x direction. So it's shifting left and right, okay? This is on the outside. And when numbers are on the outside, it affects the y values. So that means it's going to be shifting up or down in the y direction. So this is a shift up 4 units. So again, I'm going to take these points where change is happening and go up 1, 2, 3, 4. And I'm going to go up 1, 2, 3, 4. And take this point 1, 2, 3, 4. So it looks something like this. 1, 2, 3, 4. All right. So there is my graph B, up 4. All right. Two things happening. This shifts left 1. The -2 on the outside shifts down 2. So again, I'm just going to go to my little 4 corners here, 4 points, and say go left 1, and then go down 2. And I'm about right there. Left 1, down 2. I'm going to go to this point, go left 1, down 2. And my very last point, left 1, puts me in the middle, and then down 2, and connect the dots. When I do this again next year, I'm going to change this graph because it's just not complicated enough. All right, so this is graph letter C, I'm calling it. All right, now we're having some different things here. We're multiplying. We're no longer just adding and subtracting. Now we're multiplying. And this, again, let's see, I even have more colors. I'm just going to go color crazy today. This is 2 times the function. And again, would you say that the 2 is on the inside or the outside? It clearly looks like it's on the outside. And since it's on the outside, it's going to change the y values. Everything on the outside changes the y's. So in this case, it's taking the y values and it's multiplying them by 2. 2 times the y values. All right, and so I'm going to go back to my original boring black f of x function, and it's going to take here, this point. The y value is -3. It's going to do 2 times that value. Well, 2 times -3 is -6. So this is called a vertical stretch. It's stretching vertically. Vertical stretch by a factor of 2. So a factor, the word factor just means multiply by a factor of 2. So what did we multiply by? We're multiplying by 2. I'm going to go to this point here. Again, this point was at -3 on the y-axis. So the output, the y value is -3. And when I multiply that by 2, it becomes -6. This point on my original graph, the y value is 1. When I multiply that, it doubles, becomes 2. This point again has a y value of 1. 1 times 2 is 2. So you can see how the graph is stretching taller. I need a straight edge for this. That's just too far. Look at me with my tools right at my arm's reach. All right, there it is, ladies and gentlemen. So this is graph D. You can see originally the range was from -3 to 1. But now the range is doubled, going from -6 to 2. All right, so everything expands. The range also doubles. All right, here, let's use pink. Here, this too, inside or outside? Inside with x. So it is affecting the x values. Here's the problem. Remember, everything with x is opposite. X is backwards. I'm going to say backwards. I don't want to say opposite. X is always backwards. Backwards land, okay? And so even though it says it looks like we're going to multiply the x values by 2, that's not actually what happens. Again, everything with x is in opposite land. It has to do with solving, okay? We're like solving for x. We have to undo everything. And so to do that, what we actually do, this is not multiplying the x by 2. It's actually flip the fraction. We're actually going to take those x values and multiply them by a half. So that's what we're going to do. We're going to flip the fraction and those x values get multiplied by a half. So if you're taking a number and you're multiplying it by half, it gets smaller. So this is actually a horizontal compression. Because we're multiplying by half, everything's going to come smaller. And we're doing this in the x direction. So this is where our function actually shrinks closer to the origin, okay? Horizontal compression by a factor of 1/2. And so again, we're multiplying by a half. We're not multiplying by 2. We're going to flip it, flip the fraction. So let's look back at our original function here. This is kind of a terrible one for this. We're here at, I'm going to say that that's on the x-axis negative 6.5. We want half of that x value. Half of that x value would be 3.25. So this point is compressing by half and coming to about right here. Right, so it's pulling in towards the y-axis. It's compressing horizontally. This point on the x-axis is here at -4. It's going to compress halfway. So it's going to compress and move horizontally to -2. So it just slid it to -2. This point is at 2 on the x-axis. It's going to multiply by a half. 2 times a half is 1. So again, you see how it's compressing. And here again, we are at like 6.5. That's going to compress to about here at 3.25. So you can see this function, very interesting. There it is. I'm gonna highlight that one because it's kind of hard to see. So I'm just gonna highlight. There, that one, highlighter one. So it's very, you can see how it was very big before, and now it's half as long as it was. So if before we went from -6.5 to +6.5, oh, I totally missed this point, didn't I? It was supposed to start there. Oh, whiteout, where are you? Ah, okay, here. Boop, that was not right. Oh, well, now this is just totally foobarbed. So it went from here, 3.25. That was that pink dot I was supposed to get. There we go. All right. So, well, that's not great, but see, so that's why I love my pens. They actually, you know, erase. All right, we all make mistakes, ladies and gentlemen. This is all make mistakes. Okay, so now we went from negative like 6.5 to positive 6.5, and now we're half as big. So we're going from negative 3.25 to positive 3.25. Okay, so shrinks by a 1/2 factor. All right, so f of negative x is, again, that negative is inside with x. This is a horizontal reflection. That's a term specific to Mrs. G. I've never really seen that written anywhere in any other book, but I think it, you know, you look at your blue graph and you're just reflecting it horizontally. Really what's happening is your x values are all becoming the opposite. So I don't have a super color for this. Let me try this. A lime green. Here's a lime green. Let's see what happens here with lime green. So this horizontal reflection, here's this point at negative 6.5. That is going to turn to the opposite. The opposite x value becomes positive 6.5. Here's this point at -4. It turns negative. It changes sign, becomes positive 4. Here's our original point at 2,1. The x value turns opposite, becomes -2,1. Here's our point at positive 6.5, turns opposite to -6.5. So there, crazy graph, right there. That is letter F. All right. And then I guess I'll use Sharpie. That one didn't show up too well. Last one. This is the negative on the outside. That's going to affect y values. That's going to be a vertical reflection. And again, those y values just become the opposite. So here is our first point. The y value was -3. That's going to reflect over the x-axis and become +3. Here again, this point on the graph is at -3. It reflects over the x-axis and becomes +3. Here's our point at +1 on the y-axis. It reflects over the x and becomes -1. And again, +1 flips and becomes -1. So this just gets flipped, turned upside down. How became the prince of a town called Bel Air? All right. And that is G. Hopefully you remember that, and hopefully this was a good review. It's a lot. It's a lot all in one. Oh man, and we're just not done yet. Okay. Last one. An open box of maximum volume is to be made from a square piece of material 24 centimeters on a side. Stop, draw a picture. So I have a square piece of material. It's a square. What does that mean? All 4 sides are equal. And they tell me that they're 24 centimeters on each side. 24, 24, 24, 24. Never read a problem straight through. Never, okay? We're going to try and do a lot of applications because that's half of your test on the AP test are word problems. So that's the free response. Everything is a multi-part word problem. So you need to take your time, draw a picture, read 1 sentence at a time, and process 1 sentence at a time because there was a lot going on in that 1 sentence. So take your time, draw a picture. Open box, a maximum volume is to be made from a square piece of material 24 centimeters on a side by cutting equal squares from the corners and turning up the sides. So they're going to cut out equal little squares here, these little guys. They're going to cut out this edge from every single corner here, these little squares, and then like fold up these edges. And so we'll remove these little corners and then be able to fold up the sides and create a nice little box, an open top box. Open top box. All right, write the volume V as a function of X, the length of the corner squares. So these little lengths here that they're removing are length X. So what's going to happen is we're going to fold up those sides and we're going to get this box. I'll show you just, we turn up the sides and create this open top box. Yes, if you're not good at drawing 3-dimensional shapes, you're going to get good, okay? And so what we have here is this length X. That's that height that we create in the box. But let's figure out what is. We know the whole length started as 24, but we cut out this length X, and we cut out this length X. So then we want to know what is, when we fold up that side, we cut away that material, how long is this remaining piece here? We took away an X and we took away an X. The whole thing was 24 and we took away 2 X's. And so each little length here is 24 minus 2X. And that's the same thing on each side. We started with a full length of 24 and we removed this little piece X and we removed this little piece X. We take off the corners, so we subtracted 2 X's. So, and then this little length is 24 minus 2X. Okay, so how do we find the volume? The volume in terms of X is length times width times height. So x times 24 minus 2x times 24 minus 2x. And this is a great volume. Do you need to do any more? Do you need to multiply it together? No, you don't. And in the AP Calc test, they're not going to want you to, because what if you made a mistake? This is perfect. If you try and multiply it out and think 24 times 24 is 48, you just did that wrong, and now it's not right, and you can't grade it, and you don't get any credit for all your work. So we're just going to leave it like this. What is the domain of the function? That's very interesting. So what possible values could x be? Well, let's think that through. Could x be 0? 0 doesn't make any sense. Can I remove nothing? Then I can't fold up any sides either. So 0 doesn't make any sense. But anything bigger than 0, technically, I guess, would have a tiny, tiny, tiny height, maybe. So anything bigger than 0, it seems, would work for x. Can x be a negative number? Can we subtract the negative length? No, that doesn't make any sense. Okay, so x needs to be bigger than 0. It can be 1. So if x was 1, we'd be taking off 2 centimeters. Okay, that makes sense. Could x be 3, 4, 5, 6, 7, 8, 9, 10, 11, 12? What happens when x is 12? If x was 12, I'd be removing 12 centimeters of material on one side and 12 centimeters of material on the other. That wouldn't leave us with any box again. We just lost our material to fold up, so that doesn't make sense. So it looks like the domain of this function, x needs to be greater than 0 and less than 12. Absolutely. So that's one way we could write it. If we wanted, this is inequality notation because I'm using inequality symbols, but we could also say that x had to be between 0, 12 with parentheses. So that's the same way to say it. All right, now we want to use a graphing calculator to approximate the dimensions of the box that yield a maximum volume. Well, let's graph this and see what it looks like. I'm going to use my TI first. I'm going to go to my graphing menu, and I'm going to plug in x is 24 minus 2x times 24 minus 2x. I'm going to do a zoom standard window. And that was interesting. I'm going to go how we already talked about the domain needing to be between 0 and 12. I'm going to change my window. I'm going to make it go, I'm going to say like -2 to maybe like 15. And the volume's going to be fairly big. I'm going to make my y maximum a lot bigger. I'm just going to guess. Let's see if something happens if I say that x maximum is 100. We're talking about volume. It's going to be bigger. Let's see if I see anything now. Oh, hey, I got something. Okay, that's good. I want to see some more. I think I want my y maximum to be taller. So I'm going to change my y maximum. I'm going to try 500. Oh, now I really see something. Oh, interesting. So sometimes it's a guessing game, ladies and gentlemen. If we were to multiply all of this together, 24 times 24, what is that? Big. Let's see. I don't know that math. I think it's 576, but oh, I was right. It's 576. So I think I need to go at least as big as 576. So I'm going to try 600. Let's see if that works. Oh, even bigger. Still bigger. I need to go bigger. All right. I want to see the top of that curve. So I'm going to keep playing with my window. And in your Casio, you're playing with your viewing window, V window. So let's graph that. I went to 1,000. Oh, not quite there. Okay. So you can see it's a cubic. That makes sense. Volume is cubed. Oops. I'm going to go to window, make it a little bigger. Let's try 1,200. So we need to be able to modify our window to see what we're supposed to see. This is volume. Volume is a cubic. That's why the units are cubed. centimeters times centimeters times centimeters, centimeters cubed. So the volume changes in a cubic manner, okay? And this is the cubic polynomial, starts low, ends up high. And we can see right here is where we would get a maximum volume. So we want to find that maximum. The Casio is super easy to do. On the TI, not so much. So if you use your calculator in this manner, it's a great idea to communicate your window that you're using to your grader. So you need to label your window. And our window, the x-axis went from -2 to 15, and the y-axis went from -10 to 1200. And you can see that I'm just making those markings. Every AP grader is going to understand what you're doing. And then you're going to make a quick sketch. And it doesn't have to be beautiful, but something like this, and your AP grader is going to know what you're doing. They're going to understand your thought process, and this is great. And then we're going to use our calculator to calculate the maximum. So you're going to go to the calculate menu. You're going to go to second, calculate. We want to know the maximum. That's number 4. It's giving you a whole slew of processes that you have to follow. It's saying left bound. That means you need to move Tinkerbell to the left. So we're going to go left, 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 left until Tinkerbell is past the maximum. You need a left boundary. How far does the calculator need to look to the left? Okay. And then hit enter. And now it's saying we need a right boundary. So you need to go right, past the maximum. And it wants to create some boundaries so it can search for that maximum Y value, that maximum volume. We're going to hit enter. And then you're going to guess, and you're going to put Tinkerbell at the top and hit enter. So it's a left enter, right enter, enter. All right, and so this maximum is at 3.9999. What is 3.9999997? 4. That's round off error on your calculator. 1024 is the maximum. And so we want to use a graphing calculator to approximate the dimensions of the box that yield a maximum volume. So the dimension is here when x is equal to 4. When x is equal to 4, let's draw that. Drawing three-dimensional figures is all about parallels. What's line? So here was our x. That was our height. So if this height is 4 centimeters, then 24 minus 2x, that would be 24 minus 8. 24 minus 8 is 16, and this would also be 16. So the dimensions would be 16 centimeters by 16 centimeters by 4 centimeters. And it doesn't matter what order those are in, okay? So, very interesting problem. And hopefully you figured out how to use your calculator. That's it. I'm going to show the Casio. We're going to go to the graphing menu. I'm going to delete this. If you want to go on to Delta Math, you can stop the video. If you have a Casio, you're going to want to watch x. I'm going to type in my equation, 24 minus 2x. And again, 24 minus 2x. And we've already played around with the window. If you press graph, you don't see anything. That doesn't mean you did it wrong. It means that your window isn't good enough. So again, we talked about the domain of the function. So we want to go to viewing window. It's a yellow on my calculator. So we do shift V window, viewing window. And we're going to play with those values. So I said before, -2 on the x minimum. The maximum was 15. And you have to hit execute. My y minimum, we said, was like -10, and the maximum was 1200. Execute. Then you can press exit and draw, and now you can see the window. So it's playing around with the window. You need to get comfortable with that. Now I believe your calculator is so much easier. You see graphing solve. So we're going to do shift graphing solve, and we want to find the maximum. Look at that, so easy. You have all these things intersect, y-intercept, minimum, maximum. We want the maximum. You're gonna press maximum, and there it is at 4:10:24. It's so awesome. The Casio is a great calculator, I swear. Okay, so that's your maximum value. You know, it's great. So easy. So there you go, using your Casio, using the TI. Ladies and gentlemen, I hope you found this helpful. Go ahead and give your Delta Math a try. Bye.